We talked about basic notions of probability, and if anybody has a particular question, now is the time to ask it. And don't be shy. No questions. Am I doing such a great job that everything is so clear and perfectly simple? Or are you guys just too shy to ask questions? All right, well, they'll come up in context. So remember, there's just a few axioms with respect to probability theory. Namely, a probability is always a number between 0 and 1. Probability of the sample space is 1 if A and B are disjoint, then the probability of A union B is equal to the probability of A plus the probability of B. In general, when they're not disjoint, the probability of the union is equal to the sum of the probabilities minus the intersection. The probability of the complement is 1 minus the probability of the event itself. And somewhere or other, I must have said it along the way, the probability of the empty set is 0. The probability of the sample space is 1. Those are the basic axioms and results we've gotten from the axioms. And then we looked at a special case of the so-called uniform sample space. Also called the equiprobable space. And there we're assuming, of course, that the sample space has a finite number of sample points in it. And then we showed if A is any event, the probability of any event in a uniform sample space is just the number of ways A can happen divided by the total number of things that can happen in the sample space. And as a trivial example, suppose I have a deck of cards. And I draw 4 cards. Determine the probability both are aces. Okay, I'm assuming you're all familiar with the deck of 52 cards. So basically what I really have here is an urn, if you like, or a deck of cards. I have 4 aces in my deck and 48 other cards. Okay, 48 others. And I'm drawing 4, meaning without replacement. Well, the way I can draw 4 cards from the 52 is this number. That's the total number of ways I can draw, or what I'm really saying is the number of ways I can choose a committee of 4 from 52 is 52 choose 4. Now, I have 4 aces. So the number of ways I can draw 4 aces, if A is the event of drawing 4 aces, from the 4 aces, I'm drawing 2 cards. That means from the 52, from the 48 other cards, I'm also drawing 2. Let me say this problem another way, okay? And then we'll finish it up. Think of my having 4 men and 48 women, and I'm choosing a committee of 4 containing 2 men. It's exactly the same problem. So I need to choose 2 men from the 4 2 women from the remaining 48, and in total, I'm choosing 4 from the 52. So that means the probability of this event, I call the event A, would be 4 choose 2 times 48 choose 2 over 52 choose 4. Remember, when I'm doing this problem, I'm assuming the probability of choosing any card is equally likely as any other card. Anybody have any question about this example? And this is an example of something I call hypergeometric probability. This kind of problem. Notice the tops, 4 plus 48 add up to 52, 2 plus 2 add up to 4. And again, that's the hypergeometric. So that was just a quick review problem involving simple probabilities. So one more example. Suppose I have 5 men and 4 women, and I'm going to stand them in a line, or take the picture in a line. Determine the probability they alternate. No, this is really a counting problem that we did earlier in the semester, but now what I did, I couched it in terms of probability. Well, first thing I know, there are 9 people, so the total number of ways they could stand in a line is 9 factorial. The total number of ways this could be performed. Now, I want them to alternate. Now, I can only start with a man because watch, if I put a man here, a man here, a man here, a man here, and a man here, that takes care of 5 men. I couldn't start with a woman. And by the way, this is 5, 4, 3, 2, 1. Now, I couldn't start with a woman because I only have 4 women. So in order to alternate, I have to start with a man. And now we put in the women, 4, 3, 2, 1. So we have, notice this numerator is just 5 factorial times 4 factorial. So the required probability is just 5 factorial times 4 factorial over 9 factorial, which is easy to work out, by the way. 5 factorial, 4, 3, 2, 1, 9, 8, 7, 6, 5 factorial. This cancels this. 4 and 2 is 8. 3 and 6 gives me a 2. So what does that give me now on the top? I think I'm left with a 1. On the bottom, I have 9 times 7 times 2, and whatever the answer is, that's easy enough to multiply through. So there were some simple examples involving basic probabilities. Notice all I really was doing was counting, and that's why we needed to know how to count. Okay. Then the last thing I did, I began on Wednesday, is I talked about conditional probabilities. So what's the probability? This was there at B given A. So this is red. The probability of B, this word right here is given, or if, given A occurs. So that means you're given additional information. You're given A, and you want to know what the probability that A occurs. For example, I think I did an example like this the other day. Suppose the sum of a pair of die, when you toss a pair of die, suppose the sum of a pair of die is 8. Determine the probability one of the dies is a 3. So now you're given A. A is the event that the sum is 8. Now, the only way the sum could be 8 is, let's see, we can have a 2 and a 6, a 3 and a 5, a 4 and a 4, a 5 and a 3, a 6 and a 2. And B is getting an 8. Now, the probability of B given A is really trivial. Look at this. The only way, so what's happening now is the sample space is being reduced. Instead of looking at the entire sample space, it's as if A is now the sample space, because you're being told this happened. You're being told the sum is 8. Well, the number of ways that can happen is 1, 2, 3, 4, 5 out of 36, right? And out of these 5, the only way you can get a 3 is this way or this way. 2 ways out of 5. Now, I showed you the other day that one can actually have a formula for this. Because if you actually look at this, notice if the sum is an 8, look at all, where did this come from? If you look at all the possible ways you can get an 8, then you would see, suppose I wrote out all the 8s. How can I get an 8? I'm sorry, B is B is, if you look at all the ways you can get a 3, you get a 1, 3, a 2, 3, then you get 3, 1, B, 3, 6, and so on. Now, it turns out that the intersection of B with A is just these 2 events. If you wrote out all the ways you can get a 3, the intersection, this number 2, is just really the intersection of A and B divided by P of it. And I think I showed you this with a Venn diagram the other day as well. So in general, we define the following formula. But notice I didn't need this formula to do these problems. The intersection divided by what's given. Or sometimes they write it this way. You're given B and one of A. It's the same result. B intersection A is the same as A intersection B over P of B. And the assumption, of course, that the denominator is not 0. So we have the following definition. The probability of A given B is equal to the probability of A and B divided by the probability of B, under the assumption, of course, that the probability of B is not 0. That's positive. Now, I want to emphasize, for most typical problems, you don't need to use this formula to figure out the probability. Example, here's an urn. I have 6 red marbles and 8 blue marbles. If the first marble is red, determine the probability the second marble is red. So given the first marble is red, what's the probability that the second marble is red? Well, if the first marble is red, what's left in the urn? 5 red and 8 blue. So if the first one is red, the probability the second is red will just be 5 out of 13. There's nothing to do. It's sort of a trivial problem. It's because they told you what happened, you know what's left. Do I need to use a formula here? I could. If I wanted to use the formula, what would it be? It would be P of R2 intersection R1 over P of R1. In fact, let me show you. Well, and then I can figure this out. This have to be whatever it is, and this would put down probably the first is red. I'll show you how to do this in a couple of minutes. So let's analyze this a little bit more, and then we'll look at some examples and show you that even though there are formulas, you don't need to know the formulas if you know how to draw a tree diagram. So let's look at P of A given B. This is equal to P of A intersection B over P of B. Now, if I cross multiply, what do I get? I get P of A intersection B is equal to P of A given B times P of B. And this is often called the multiplication formula for probabilities. Notice P of A and B is not equal to P of A times P of B. It's equal to the conditional probability of A given B times the probability of B. So here's what's happened. Let's suppose B happens first. I want to illustrate this on a picture. And on this branch of the tree, I'll label the probability that B happens. And then A happens. So this number is given B, the probability of A. By the way, if I want to complete this tree, now look at this event. I claim if I get to this branch in the tree, this is P of A and B. Why? Because of the formula I have above here. So notice, if we follow the path, we end up with the appropriate probability. So let me walk through a very simple example to illustrate this, and I'll show you how we can generalize this formula without memorizing any formulas. So let's suppose I have an urn, and in my urn, I have 9 red and 6 blue marbles. I draw 2 without replacement. I ask the following question. Determine the probability A. First is red. B. First is red and second is blue. C. Both red. D. The second is red. So I'm asking a couple. So let's look at this. So what can happen on my first toss, on my first drawing? The first one could be red, or the first one could be blue. What's the probability that the first marble drawn is red?
1 out of 15.
9 out of 15, right? There are 9 reds, so I have 9 possibilities out of 15. So this is 9 out of 15, and this is 6 out of 15. Now at this point right here, I'm assuming the first marble is red now, okay? Well, if the first marble is red, what's the oops. The second can be red or blue. At this point in time, right here, how many reds are left in the urn?
8.
Drew one already. So how many are left?
It's probably 8. Eight
Out of-
left is out of 14.
Right, and then number of blue would then be,
Blue
of
would
14.
then be
by the way, notice that every node, the sum of the probabilities will always be 1, because one of two things has to happen. Notice 8 over 14 plus 6 over 14 is 1. 9 over 15 plus 6 over 15 is 1. Okay, similarly, if the first marble was blue, then they're going to be, the second could either be red or blue. Well, if the first one's blue, there's still 9 red out of 14. And if the first one was blue, there are only going to be 5 out of 14 blue left. So now I completely labeled my tree. So now let's answer the questions. The probability that the first marble is red, well, that was trivial. It's just going to be 9 out of 15. Or if you like, 3/5. The probability that the first is red and the second is blue, well, where am I on the tree? For that to happen, if the first is red and the second is blue, I got to be here. And that's by the multiplication principle that I just gave you. If I wanted to, I could write the formula. The formula would be the probability that the second is blue, given the first is red, times the probability that the first is red. But I don't really need the formula if I understand how the tree works. If I want the first to be red and the second to be blue, I must be here. And so by the multiplication principle, it'll just be 6 over 14 times 9 over 15. And that would be my answer, which I'm not working out. Okay. The next question, what's the probability that they're both red? In order for that to happen, I have to be right up here. See the asterisk? Let me for this to happen, this must happen and this must happen. So again, by the multiplication principle, that's 8 over 14 times 9 over 15. And that would again be my answer to this particular problem. What's the probability that they're both red? That's the probability that the first is red and the second, and the second is red. Didn't I just do that? I'm sorry, I'm doing the wrong problem. I just did that. Let me quit.
Then we shall be moving forward to the second ball is red.
Oh, second, I'm sorry. I'm sorry. The question I asked was, the last question was, what's the probability that the second is red, correct?
Yes.
I did both red. Okay. So what's the probability that the second is red? So let's point out, this could happen 2 ways. How could this happen? The first could be red and the second could be red. Or the first could be blue and the second could be red. Everyone follow that? It can happen 2 different ways. In order for the second to be red, 2 different things can happen. I can either end up here, or I can end up here. So I have an alternative number of ways of performing the event. Notice these 2 events are mutually exclusive. So since they're why they're mutually exclusive? Because if you take the intersection, the first one can't be blue and red at the same time, for example. So this is equal to P of R1 and R2 plus P of B1 and R2. Notice it's the same kind of addition principle that we had for sets or in counting. It's the alternative principle. If there are alternative ways of getting a probability, it's going to be the sum of the probabilities. Now, each of these is obtained from the tree. R1 and R2, we already did. That was what? 9/15 times 8/14 right here. This was 8/14 times 9/15. And the first is blue and the second is red. I didn't do that one yet. The first is blue and the second is red. That's this path right here. So that's 6/15 times 9/14. And the sum of these numbers is the answer. So let's look at another example. I want to make sure you follow this. Where's my book here? Oh, I want to remark that I showed you a couple of minutes ago that the probability of A given B is equal to times the probability of B is equal to the probability of A intersection B, the so-called multiplication principle. Now, I could generalize this. First, let me just draw a picture of this in the case we just considered. So if this is B, this is the probability of B. And then suppose A follows. This is the probability of A given B. And right here, the event is A intersection B. I can draw the other ones if I want. I'm not interested in those right now. So notice the probability of A intersection B is just the product, according to the definition of conditional probability, of P of A given B times P of B. So that says, if I want to find this probability, I just have to multiply along the path of the tree, the branches of the tree to get the probability. It's just P of B times P of A given B. Now, this law, this formula generalizes, and it generalizes as follows. Let's suppose I had, let me just change the notation a little bit. A, I'll call it A1. A2. A3. I don't really need all this stuff, okay. So here's the probability of P of A1. This is the probability of P of A2 given A1. And this is the probability of A3 given A1 and A2. And the event right over here is A1 intersection A2 intersection A3. So if I wanted a formula for P of A1 intersection A2 intersection A3, if I follow the path, starting with the last one first, it's P of A3 given A1 and A2 times P of A2 given A1 times P of A1. I mean, I can prove this very generally, by the way. If you want to actually give a formal proof of this, call this event B. Then,
Professor, is it possible you can make your pen more finer?
yeah, let me see what I can do on that. Where am I now? Let's see what that was. So again, let's rewrite. So P of A1 intersection A2 intersection A3, therefore is just P of A3 given A1 and A2 times P of A2 given A1. I think the problem not to find this is my handwriting, times P of A1.
No, it's much
Now,
better. I think it's
this
much better.
formula, I could derive it very easily, but it's really based on your understanding of what a tree diagram is and how we're now using tree diagrams to represent probabilities. So let me do another example, which will illustrate this again. Where am I? Okay, so what do we have here? So I have a box of light bulbs, okay? Now in this box of light bulbs, I have, they're indistinguishable. And how many do I have? I have a box of 8, okay? There are 8 of them. And 3 are defective. By the way, I should remark in the last problem and this problem as well, I could do parts of this using combinations and counting as well. I don't need always to use trees. There's more than one way of doing a problem. I'll illustrate that along the way, okay? So here's the question. A box has 8 distinguishable light bulbs, 3 of which are defective. 2 are selected at random. Okay, I'm selecting 2 at random. Determine the probability both are defective. And then I ask you to repeat the problem if I select 3. Okay. So what's the probability that they're both defective? Well, firstly, let me show you I can do this problem very easily using combinations. If I have 8 light bulbs, the number of ways I can choose 2 is just 8 choose 2, right? If I have 8 people, I want to choose a committee of 2, number of ways is 8 choose 2. Now, if I want them both to be defective, how many light bulbs are defective? 3 of them are defective. I'm choosing 2 from that group. And by the way, technically, from the other 5, I'm choosing none. I don't really need that number because that'll turn out to be 1. So the answer will just turn out to be what? 3 over 8 times 56. 3 over 28, is that, if I did that right? So I could have done this problem without doing any tree diagram at all, but I can ask different kinds of questions. I want to illustrate an idea here. Okay, so the other way of doing this problem is the first one can be defective, or it's not defective. Let's see. How many defective are there? There are 3 out of 8, right? So this is 3 out of 8. This is 5 out of 8. Well, if the first one is defective, how many defectives are left in the urn, in the bag, in the box?
2 out of 7.
2 out of 7. Okay, let's draw our tree. Whereas if the first one is not defective, the probability of the second one, there's still 3 defectives out of the remaining 7. And this would be 5 out of 7. I'm sorry, 4 out of 7. Remember, at every node, the numbers add up to 1. So the probability that the first is defective and the second is defective, if I wanted to use a formula, let's clean that up. So the probability of the first, they're both defective, the second and the first are defective. If I wanted to use a formula, is P of D2 given D1 times P of D1. But notice I don't really need the formula. They're both defective, I got to be here. And by the multiplication principle, that's just 2/7 times 3/8, which turns out to be 3 over 28. So there was a very simple way of doing the problem, without a tree. Okay, so let's ask another problem. Now the same problem, except I think I draw 3. Yeah, okay. So now we draw 3. I don't really need to draw the whole tree because now the question, what's the probably all 3 defective? I just need to know how many do I have? I have 3. There are 8, okay, 8 and 3 are defective. Okay, so the first one is either defective or it's not defective. That probability will be 3 out of 8. The second one will be defective if the first one is or not. Now there are 2 defectives left out of 7. Notice I'm not drawing the entire tree. I'm just drawing the tree that I need to get to the event that all 3 are defective. So here's the event where they're both defective. So that would just be all 3 are defective. It's just 1/6 times 2/7 times 3/8. So that should give you 1/56. Notice it was a relatively straightforward problem to do. And I really didn't have to work hard at all. Let's look at another example where I'll add a little complication to it for you. Okay, so let's suppose I have an urn. I have 6 red marbles and 4 blue marbles. I'm going to choose 2 without replacement. Remember, without replacement means either I'm drawing both simultaneously, or if I pull one out, I don't put it back into the urn before I pull the next one out. So let me ask some questions. Determine the probability. A, both are red. B, the probability the first is red or the second is blue. Okay. Well, let me draw, again, I'm illustrating trees here. I'm illustrating conditional probabilities. So let's do the following. The first could be red or it could be blue. What's the probability that the first is red? 6 out of 10. Probability that the first is blue is 4 out of 10. If the first is red, there are only 5 more red left out of the remaining 9. So this must be 4/9. If the first is blue, there's still 5 red left out of the remaining 9. And blue would then be 3 out of 9. So there's my tree. It has all the information I need. So the first question is, what's the probability that they're both red? And there's nothing new here. I have to get to this position right here for them both to be red. This is the end R1 and R2 at this spot. And that would just be by the multiplication principle, 5/9 times 6/10. 1, 2.
Is 1/3, Professor.
Sorry, I said without replacement. Yeah. With replacement, all the numbers are always the same. Okay, and if I want to make this look pretty, 1, 2,
Is 1/3, Professor.
which is 1/3. Yes. Okay. So there's the first question. Now the second question says, what's the probability? The first is red, or the second is blue. So I'll show you how to do this two ways. First is red. I'll show you how to do it three ways. First, if you want to blindly use a formula, it's P of R1, the addition formula, plus P of B2, minus P of R1 and B2. Okay, what's the probability that the first one is red? 6 out of 10. Oops. But what's the probability that the second is blue? Well, the second can be blue how many different ways? It can be blue this way, see it? Or this way. And each case has a product here, so it would be plus 4 out of 10 times 3/9 plus 6/10 times 4/9. Again, this path or this path. Minus the probability that the first is red and the second is blue. That means I got to get here. That's 6/10. Oops. 6/10 times 4/9. And you can do the arithmetic, you'll get the answer. So there's one way of doing the problem. Okay. Now here's another way, and then I'll show you a third way. So here's method number one, method number two. Notice in the problem I just did, I asked what's probably the first is red or the second is blue. That means I'm either here, here, or here, right? Those are the three cases I just considered here. Everybody see that? I'm either here, because here the first would be red. Let me make sure I can either be here, here, or here. What's the only case that's missing? The only case that's missing is this case. So by complementation, it's 1 minus 4/10 times 5/9. That would be 2, what was that turn out to be, 8/9? So again, what I did is, instead of doing the computation number one, which ended up essentially looking at three cases, I looked at the complement. Now here's the third case. If we think of this as a game of chance, I win the probability if the first is red or the second is blue. Well, what's the probability that the first marble is red? That's right here. That's 6/10. So that's one way of winning. If this happens, if this event right here happens, I've won immediately. What's the only other way to win? If the second is blue, if I get here. In order for that to happen, that would be 4/10 times 3/9. So there are, as I just illustrated, three different ways of doing this problem, just by reasoning it out a little differently. How am I doing? There's one more example I do here. So let's look at it. Okay, last example of this group. So we have again, we have two urns, different variation. Two identical urns. The first urn has in it 6 red and 4 white. And the second urn has, these are indistinguishable urns. So you choose one of them at random. The second one has, I lost the place, 3 red and 5 white. Okay, so we select, an urn is selected at random. And I'm drawing a marble. Okay, so I choose an urn at random, and then I choose a marble. Determine the probability the marble is red. Okay, so here, the first thing I have to do is choose an urn. So we have urn 1 and urn 2. If they're identical and they're chosen at random, what's the probability that I choose either urn? So if I'm selecting an urn at random and there are 2 urns, what's the probability I choose either urn? Yep. Now, if I choose urn 1, I either get a red ball or a white ball. The probability of getting a red is 6 out of 10. A white is then 4 out of 10. If I choose urn 2, the probabilities are 3 out of 8 and 5 out of 8. So now the question is, what's the probability that the ball I choose is red? Well, we see it can happen 2 ways. Here's one path. Here's the other path. So it would be 6/10 times 1/2 plus 3/8 times 1/2. And this solves the problem. If for those of you who like answers, maybe I'll ask another question here as well. To do the arithmetic, the answer turns out to be 39/80. Okay. Suppose I ask you a different question, the same question I asked a minute ago. Determine the probability either it's red or urn 1 was chosen. Let me call that answer little p. Well, if I do it the quickest way I like, the probability I choose urn 1 is 1/2. Okay, so if I chose urn 1, I've satisfied the requirement of the problem one way, so I don't have to go any further. Once I get to this point, I don't have to go any further. On the other hand, if that didn't happen, how else can this happen? Well, it can happen if I get to here, and that's equal to plus 1/2 times 3/8, and that would give you the answer. Okay, here's another example, which is an interesting one that a result I'm going to need later. Let's suppose I have an urn, and in my urn, I have R red marbles and W white marbles. Determine the probability the first marble is red. Second marble, I keep on drawing. Second is red. Third is red. And so on. Let's see what happens here. Okay. Well, red or white, right? This has R red, so this would be R over R plus W, correct? So the probability that the first is red is R over R plus W. Now let's go further. So I've answered the first question. What's left in the urn are R minus 1 reds, right? Because originally there were R reds and I chose one. Now what's left is R minus 1. And this would be R minus 1 plus W. Everyone follow this? If there were 20 red originally and 15 white, then the first would have been 20 out of 35. Now it's going to be 19 out of 34. So the probability, and by the way, I need this. So this would be R over R plus W minus 1, right? Because if the first is white, there's still R red left. So the probability that the second is red will be R minus 1 over R plus W minus 1 times R over R plus W plus, oh, by the way, I should have written this number too. This is W over R plus W plus R over R plus W minus 1 times W over R plus W. So let's do a little bit of arithmetic. I can take, so what do I have? I could factor out an R plus W minus 1. That takes care of this. Times R plus W. Something's not right. That's my denominator. And here I have R squared minus R plus R. R squared minus R. Something is wrong. Let me see what I did wrong. Let me clean this up and do it again. Let me make sure I didn't make a mistake. Easiest way is to handle this. Okay. Let's do this a little clearer. Okay, so now the probability that the second is red can happen two ways. The first can be red and the second can be red. So this is R times R minus W over R plus W times R plus W minus 1. Or it would be RW over R plus W times R plus W minus 1. Now, what the answer is supposed to be when I'm done with the algebra is just supposed to be R over R plus W. So let me look at that and see why I'm not getting that. So the numerator is R times R minus W plus RW is that right? Or R squared minus R plus RW. Why am I not getting this right? Okay. Let me factor an R out of the numerator. That'll give me R minus 1 plus W. And in the denominator, I have R plus W minus 1 times R plus W. Notice this term cancels this term, and I get R over R plus W. So notice the probability that the second is red is also equal to R over R plus W. Now, I claim the following. If you do this n times, it's a little messy to prove, but what's going to happen is the probability the rth marble is red is always the same. So let me make sure you understand this. If I have a bunch of R marbles, R red, and W white, and if I choose K marbles, where K is less than R set, the probability that the kth marble is red will always be R over R plus W. So if I had 100 white and 200 red, say, the probability that the 87th marble is red will just be 200 over 300. It'll always be the same. That's an interesting result, by the way. Does it surprise anybody? Now, how would I prove it formally? You know, technically, if I continue this tree, if I continue this tree and did the work and did all the algebra, that is, you want to get here or here, it's a mess of algebra, and one can show that the third one would be red, but the question is, how do you do it in general? And to prove it in general, use something called mathematical induction. You show it's true for, say, n equal 1 or n equal 2, assume it's true on the kth drawing, then you can then you can prove that it happens for the next drawing as well. Now, that's a really interesting, very interesting idea. Okay, so how's my time? Maybe I'll mention one other fact. As far as the exam goes, it'll be through section 2.3. Okay, so make sure you do the homework in section 2.3. On Wednesday, come in prepared with questions that are bothering you. And once you're done asking questions, I'm going to continue doing material that will be on the second exam. I'm not going to waste any time. Time is very precious to us. I want to do one last example to motivate the next topic. And here's the question, okay? Suppose I have 6 red and 4 blue marbles. And I draw 2 without replacement. Now I'm going to ask a different question. The first question is trivial. If the first is red, what's the probability that the second is red? Well, that's a trivial question. If the first is red, how many red are left? 5 out of 9. So there is nothing to do there. But now I'm going to ask an unusual question. Suppose I switch these. How could this happen? Let's suppose one of you was outside of the room for the first drawing, and all you see drawn is the second marble. And you notice that the second marble is red. So you'd like to figure out, well, what's the probability that the first marble was red? Everybody understand that question? You see the difference? In the first case, you were in the room, you saw the first marble drawn, and now you're being asked, what's the probability that the second marble is red? And the answer is 5/9. But now I'm changing things a little bit. Let's suppose you came late and you only saw the second marble drawn and you saw it was red. You want to know what about the first marble? What's the probability that the first marble is red? Now this problem has a couple of interesting names. I'll show you it's trivial, by the way, but it has interesting names. Some people call this, you're given the effect of the experiment, determine the cause. So I like to call this the effect cause problem. Some people call it the cause and effect. Some people give this a fancy name called the Bayesian problem. I'll rewrite this name much more clearly the next time. But let me just tell you, when you have a problem like this, where basically you're being given the end of the experiment and you want to know about the beginning of the experiment, the way to do the problem is to use the conditional formula. That is, P of R1 given R2, I know is equal to P of R1 and R2 divided by P of R2. This is one of the few cases where the conditional formula is really very useful. So for example, in this problem, the first one could be red. What was the other color here? Or blue. The probability it's red is 5 out of 9. This is 4 out of 9. Red, blue, red, blue. This will be 4 out of 9. Is that what I had? 9 here originally? Yeah. Oh, no, I originally had 10. I'm sorry. Oops, my numbers were wrong. So originally 6 out of 10, 5 out of 9, 4 out of 9, 4 out of 10, 3 out of 9, 6 out of 9. Okay. So to solve this problem, R1 and R2 is here. That's 6/10 times 5/9. Whereas R2 is here and here. So it would be 6/10 times 5/9 times 6/9 times 4/10. And this would just be 30 over 30 and 24, 54. 15, 2 goes 27, 3 goes 5 out of 9. I don't really care about the answer here. I just want to give you a preview of what happens next here. Namely, we can do the so-called Bayesian problem and look at the ramifications of that problem. Okay. All right, this would be a good place to stop. Please make sure you come in on Wednesday. And when you do, when you come in on Wednesday,